Okay, question 9. We are looking at a figure which shows a sketch of a curve with the equation x squared minus 2xy plus 3y squared equals 50. So we've got x's and y's in the equation, which obviously always causes alarm, doesn't it? So this is obviously, it looks a bit like a circle for me, doesn't it? But because we've got this extra little bit here, got kind of an elliptical shape. Show that dy by dx equals this. So just got to differentiate this and then get this result. Great. It's a show that questions. That's always handy. The red flag with this one here is this term in the middle. This term in the middle is the product rule. You've got 2x times y, so you've got a product there. And we're going to have to use the product rule. I just grabbed this from the internet about a nice way to remember the product rule. Write the product out twice. So your two functions, let's say, f equals, the f function equals 2x and g equals y, for example. Then you just do fgf plus fg, write it out twice, put a prime on the first one, so differential of f times g, put a prime on the second one, f times differential of g. That's the product rule. Let's see if we can use it to differentiate this. So we're going to start by, let's start by rewriting this out. We've got x squared minus 2xy plus 3y squared equals 50. And what type of differentiation are we going to use if we've got x's and y's in the equation? I'm going to use implicit differentiation, which just means whenever I differentiate a y term, I'm going to write dy by dx next to it. Okay, that's how we get round it when you've got x's and y's in the equation. We kind of always do this really, but some of you may not be aware of that. So let's just stick with this idea of write dy by dx next to anything with a y in it when you differentiate it. First thing, an x term. So I'm just going to write 2x if I'm doing the differential of that, 2x. This is being differentiated with respect to x, so nothing changes for the x terms. Minus, and then we come to this product rule. So where should we do that? Maybe let's sort the product rule out up here first, and we can write the result of that in here. So we had f is 2x and g is y. So what is going to be the differential of 2x? Well, that's just going to be 2. What is going to be the differential of y? That is just going to be 1. But I said I'm going to write dy by dx after every time we differentiate. So that'll be 1 times dy by dx, which is just dy by dx. Alright, so let's write this out. The result of this is going to be the differential of f, which was 2 from up here, 2 times the g function, which is y, plus f, which is 2x, times the differential of the g function, which is dy by dx. Okay, is everybody happy with that? I'm just checking my answer to make sure that I got the same thing, which I did. Okay, so that's fine. Now, the only problem I've got is it's minus 2, and I haven't done that up here, have I? It's minus 2xy. So I'm just going to put this into a bracket. Let's put it in there. 2y plus 2x dy by dx, and see if that holds out for us. Plus, this is going to be 6y. But I said I'm going to write dy by dx after every y term. So I'll do that in there. And 50 is just going to give us a 0. Because that differentiates to nothing. Constants differentiate to nothing. So now we've got to get this in the form dy by dx. And I have two dy by dx terms here. So I'm going to have to group those together. And then factorise the dy by dx out. So let's get on with that. let's get rid of this minus bracket here. So minus 2y minus 2x dy by dx plus 6y dy by dx. So, equals 0. Let's shift over these two terms here. So I'm going to get, I'll move the 2y over, the minus 2y becomes a plus 2y, and the 2x becomes minus 2x. That leaves me with, and I'll write this around the other way because it's positive first. I could factor out this part here. So I've got this left on the left hand side. I'm running out of space, so that's when I tend to cut corners, which is not great. I'm going to factor out the dy by dx here right now. So dy by dx. And I'm going to put the 6y in here first because it's positive, and the minus 2x there. I hope everyone's okay with that, because that is what's happening because I've run out of space. So the next line is dy by dx equals, we've got 2y minus 2x already set over here. Underneath is going to go the 6y minus 2x. And there we have it. That is pretty much almost what we wanted, but it's 2 times everything. So in the true spirit of equivalent fractions, I can get this into the correct form by dividing the top by 2 and the bottom by 2. And if I do the same to the top and the bottom, nothing changes. Alright, so we're just dividing every term on the right hand side by 2. And because it's a fraction, it will be the same fraction, just simplified. And we will have the exact format that we were after. Okay, so that's the first part done. That's worth 4 marks. Now I'm quickly going to skip to the next part. Okay, right, so let's look at the second part here. The curve is used to model the shape of a cycle track with both x and y measured in kilometres. The points P and Q are the furthest west and the furthest east of the origin, as shown in figure 4. And we've got these sort of tangents, if you like, to the curve here. And we have to find the exact coordinates of P. Now, normally, what we would be doing, if we had the gradient function, it's in terms of x. So we would normally be, if we use this version of it, we would just simply be finding the stationary points, but in terms of x. So these points here, okay, we'd be finding the stationary points here. This is no good to me. I'm not doing it in this way. I'm doing it in the opposite way. I'm doing it almost finding the minimum and the maximum as it, if y was the axis that I was working with. So I can't use dy by dx. That's not what I want to do. I don't want it in terms of x. I want it in terms of y. I want to know what the maximum minimum point is if we were doing with respect to y. So I'm going to flip that upside down. I'm going to use dx by dy for that purpose. Alright, because this is the opposite way around to what we'd be used to. And so I'm just going to write this upside down. So I'm going to have 3y minus x on the top and y minus x on the bottom. Now to find when the gradient is effectively going to be 0, now that I flip this round, you have to kind of imagine that the graph is flipped round as well. So in relation to the y-axis, alright, so if you imagine that is, I know the gradient is not 0 here, but if you were to swap them over, x and y, this would now be horizontal, if you see what I mean. Then this would also have a gradient of 0. And so with this here, and the way of solving this would give us the maximum minimum points. So let's do that. Let's set the gradient equal to 0. And let's see what values of y we would get here and here, potentially. Alright, so I'm going to write this out, and I'm going to have, if I times through by the denominator, move that to the other side, that would multiply. This whole denominator here would move and multiply with 0, which would leave you with 0. So we just get rid of it. And then you end up with x equals 3y as the result here. Alright, x equals 3y. So where am I going to put that? And how am I going to use it to solve this equation here? I need coordinates really, don't I? So I'm going to use this result. And I'm going to go back to the original equation and substitute it in there to get some coordinates out of that to see if we can get a value. Alright, so I'm going to use the original equation, which was x squared minus 2xy plus 3y squared equals 50. I can't solve this because it's got x and y's in it. I don't have another equation to do simultaneous equations. But I do have this. Well, effectively, this is a simultaneous equation. I have this relationship. 3y equals x. So I can replace all the x's with y's because I'm looking for, I'm looking for coordinates, aren't I? So it doesn't matter which way I do it really. But let's just swap out the y's because we've been talking about the y's for a bit. So 3y squared, all squared, times 2 lots of 3y times y. Just replacing every x with a y equals 50. So I'm going to get 9y squared minus 6y times y is y squared. In that middle term, plus 3y squared. This looks nice. It's all y squared, so this was actually quite a lot easier than I thought it was going to be. 9y squared minus 6y squared plus 3y squared is going to end up with 6y squared equals 50. So y squared equals 50 over 6, and then y would equal plus or minus the square root of 50 over 6. Okay, and I am running out of time here, but obviously x is equal to 3y. So if I want to know the x values for my coordinates, just put the y value back into here. So the x values are going to equal 3 lots of plus or minus root 50. No, that's going to be wrong. Sorry, it's 3 times y, isn't it? 3 times this. So that needs to be on the outside. So it's going to be x equals plus or minus 3 times root 50 over 6. Okay, so those are my x coordinates here, and those are the 2 coordinates here. Obviously this value here is going to be the 2 negative ones. This coordinate here is going to be the 2 positive results from that. I'm running out of time, so I've rushed that bit. I hope that's been helpful. I'll see you in the next video.